Chapter 6, Bending Formula Derivation Part 1. If you consider a beam at the top uh, handling a moment, bending moment, like the figure at the top, we call that a positive M. And the effect of a positive M to a beam is a push at the top section and pull at the bottom. So a positive moment pushes the top and pulls the bottom. And likewise, a negative one goes vice versa. So a negative one pulls the top and pushes the bottom. And that's a just an agreement between engineers to solve the problem in a united way. So again, if we have a positive moment and we want to see the effect on our element, so this is the section of the beam, side view of that, and this is bending stress variation. So you can easily see we have a push at the top section and a pull at the bottom. Mhm. Due to a positive moment which applies to the section. And if we want to see the effect of that on a small piece of element, so if we just consider this small piece of element and the dF applies on that and the distributed load on the area is the sigma, the stress on that. So if you want to make that a small a sample of area, so if that's in 3D, that's a volume dV, and if that's a in area, we call that dA. We are just going in 2D, so just consider that as a 2D part. So we just show that in a 3D to a better understanding of the stresses. So that's a sigma push at the top section of an element due to bending stress. Mhm. So that's pushes the top. A positive moment, which we already told, a positive which pushes the top goes by a, a positive one. So if this is positive, definitely pushes the top. Mhm. And let's expand it. Let's look at the element before deformation and after deformation. So before the formation, it's just an intact rectangle. So if you go by any part of the sample, delta S, delta is equal to delta X, there is no change from the bottom to the top. But after the formation, you can easily see delta X at the bottoms are bigger than to delta X or delta S prime at the higher sections. So why is that? That's delta S or delta S. We showed that by both. It's nothing but rho times the delta theta. That's the delta S or delta X, the original one. And delta X stand for, and delta X and delta S is the same. And delta S is rho times delta theta. But if you travel to the top by a distance, a vertical distance of y that goes by delta s prime. And delta s prime is just rho minus y. The radius is decreasing as we travel farther to the center. So that's rho minus y times delta theta. Mhm. And epsilon is nothing but delta L over original length, change in length over original length. So if we want to show that in a limit condition, epsilon x, because we were talking about delta x, delta x is a limit of when delta s goes to 0, then delta s prime minus delta s over delta s. Mhm. And if you just expand it based on delta theta, it just gives you rho my then replace delta s prime, which is rho minus y delta theta, rho minus y delta theta minus rho delta theta, which is delta s, over rho delta theta, which is delta s. Mhm. If you expand this and simplify the equation, it just gives you delta x is equal to a negative y over rho, and we call that equation 1. Mhm. Let's see what else we have. So in we know delta x is minus y over rho from previous part, and also we do know epsilon maximum is c over rho from previous parts. From Hooke's law, that's due to previous chapters as well. Chapter 5 we and chapter 6 we also review the this part. I can provide you with the video of that. Hooke's law says sigma x is a elasticity modulus times epsilon x, and that's a epsilon x times modulus of elasticity. So if you replace that with sigma x, it just gives you a negative y over c times sigma maximum, and e times epsilon is just sigma maximum, and that's our a force equation. Yep, at the same time we do need to call this is our second equation, this is our a third equation, mhm, and this is our fourth equation. Just have this four equation for we'll get back to this four useful equation in formula derivation. Now let's go to, yes, this is a third equation, which is the same equation I showed you here. And this is second equation. 1 and 2, combining them, it gives you this one. Let's finding the location of neutral axis. Mhm. If we want to know where our neutral axis, which I told you, neutral axis is where there is no pull and there is no push. So somewhere between pull and push, there is a neutral axis which there is no pull and no push, so stand neutral. So to find that, we just need to go by a resultant forces. So if the resultant forces go zero somewhere between there, it means there is no push and no pull. There is a balance between the two forces. So summation of forces goes zero. It means sigma times dA over area integration is goes to zero. Mhm. If you just replace the sigma from equation 4, which we already calculate, and that's nothing but a negative y over c times a sigma maximum times dA. Mhm. So that's a relation between sigma and sigma max, which is the force equation. Force equation, which we just this is our previous force equation. Mhm. And dA. So sigma dA is force and it goes zero. Mhm. It just gives us a let's take the constant out of the integration. So that's a negative sigma over c, sigma max over c. That's a definitely a constant that could not go zero, and integration of y dA. So if this part cannot go zero, the other should definitely go zero to give us a zero at the very end. And if you remember, integration y times dA is a first a moment of the area. Hmm? And because we were looking for neutral axis, it gives us an interesting fact. This is first moment of an area, and it just says the first moment of an area about its neutral axis is equal to zero. And why is that? That says if this is our axis and this is our area, mhm, and if this is our, for example, axis, and this is our centroid. So this is our area, and this is our distance to center from axis, for example, A. So in that sense, integration over area y dA gives you first moment of inertia. But what if this axis just passes through the center? That's in fact the case which we have here. Mhm. Neutral axis goes through the center. So that gives you there is no y, so if y goes to zero, this integration goes to zero. If centroid, if the axis passes through the centroid first moment, there has no, uh, there is no meaning for y dA because y is already zero. Hmm? In next video, we'll just expand the equation from 1 to 4 to get the final derivation. So far, we stopped by just location of neutral axis in bending, then expand it to get the uh, bending moment uh, stress equation. Thank you.